All right. So welcome everyone to the Self-Driving Cars 101 April event. I'm glad you could all make it. My name is Brent Shedd and I'm the organizer for both the LA and the Silicon Valley Self-Driving Cars 101 chapters. I'm also the CEO of Zing Robotics, which develops electric autonomous ground service equipment for airlines and cargo operators. And if you have questions about that or would like to connect on that, please feel free to reach out and we can discuss that. Today's event is about probably the most critical aspect of a lot of the autonomy out there, which is the software side of things. And the open source movement is growing rapidly. It is going to fundamentally change the landscape of autonomous mobility and to give the chance for just a huge range of other players to come in, because developing the software for autonomous vehicles and the simulation capabilities, it's so expensive. And so these solutions are going to fundamentally change the number of players that can come into this space and can compete with the likes of Waymo and some of those. So today we've got three of the leaders in this space that I'm very excited to have present. And we're going to start with Helm.ai. We have Vlad Vornosky with Helm, and gentlemen, please feel free to give a short intro of yourselves before presenting. He will be followed by Herman, who is the team lead for CARLA, which is a open source simulation. And then we'll have Christian John, who is the vice chair for the Autoware Foundation. So to keep us on track, please enter your questions into the Q&A field, and we will have time at the end of the presentations to take questions. And the event is being recorded, so you'll be able to come back and watch that, and I'll post the link to that on both the Self-Driving Cars 101 YouTube page, as well as through the LinkedIn and on the Meetup page itself. So with that, I'm going to stop talking and hand it over to Vlad, who will walk us through Helm.ai's solution. Vlad, over to you.
Thanks very much. Can everybody see my screen?
Yes.
Great. Yeah, hi everyone. My name is Vlad Gorninsky. I'm the CEO of Helm.ai. Helm is an AI software company, and we offer software-only solutions into the automotive market, focusing on L2 and L3 autonomy, but the end goal for us is L4. And a bit about me. I started working in computer vision AI about 15 years ago now, during the DARPA Grand Challenge days. And then spent about a decade in applied mathematics academia before coming back to the space a few years ago to start Helm. So to start off with, I actually wanted to share what we're able to accomplish using our approach. So we've pioneered a different type of training methodology for machine learning that we call deep teaching, that allows us to achieve a much more capital efficient process for training robust AI. And to kind of showcase that, here I'm showing a video of our autonomous vehicle doing autonomous steering on a steep and curvy mountain road in the Bay Area called Page Mill near Skyline. So it's a kind of very popular road for biking enthusiasts and drivers because of how fun it is to drive or ride. And obviously it's not an easy road to tackle, even for humans. Generally people go maybe 20, 25 miles an hour on this road. That's like roughly the speed limit. And that's actually how quickly we're driving here as well right now. The notable thing is that we're able to do this using only one camera, without using any mapping or LiDAR or GPS or any other sensors. And that means that we're really just driving based on computer vision. And the neural network that we're using here, it understands essentially exactly where the lanes are on the road. And we've kind of benchmarked this system against some of the state-of-the-art production systems, and compared very favorably. This is definitely beyond the state of the art of kind of today's available production systems. And really, the reason that we're able to do this is because of the way that we train the neural networks. So we train on about say 10 million images, and we do that without annotation or simulation. And that's very key because it's very expensive to annotate images. So typically for a supervised machine learning process, you might be paying something like on the order of dollars per image to actually get the data. Clearly, that would be financially intractable for this much data. Certainly for so for a Series A stage startup, but generally speaking, for anybody working on autonomy, because there's so many different sub problems, you can't sort of blow your entire budget on one task. And so moreover, we actually never trained on any videos that are on this road, right? So all the videos we trained on were from other scenarios. So this is actually kind of pure generalization performance and kind of a genuine, production grade test of the system, right? And that it was not at all prepared for this scenario in any kind of specific way. Of course, lane detection is only one part, one small piece of the puzzle, but the core technology that allows us to do this is actually quite general, and we can apply it to any given object category. Moreover, the one camera solution, right? That's not our necessarily preferred reference stack. That was just an illustration of what the technology can do. So we've actually used deep teaching to create, kind of a mature highway pilot system. Here we see it basically doing navigation across highways. So here the gas steering brake are automated, and we're able to traverse several highways in the Bay Area. The only input from the human here is telling the car when to change lanes, because we're not using any kind of side cameras or side radars in this particular demo, but we do have a surround view system as well. And, essentially the punchline here is that if you can tackle the perception layer of the problem really well, so if you can, interpret the sensor data very accurately, then actually building the full stack gets a lot easier. So if you can really trust the input to the system, right, for doing all the planning and control. And this is, by the way, again, this was not specifically trained for the scenario. We've driven this on many highways, and it works just as well. So in particular, we drove from SF to LA with only a couple disengagements, and essentially this is true for any given. If you pick a highway, in the U.S. or other geographies as well, we can essentially drive that. Drive that scenario. Yeah, and so a little bit as well about the company. So we're a Series A stage startup, and the team now is about 30 people. Raised our Series A last quarter, and we're currently well, we'll be making some announcements soon about our product. So I'll leave it at that. But essentially, the end goal for us is to really go after L4, right? And for L4, you need a couple of things. So firstly, there's a technological bottleneck that I think that a lot of companies have kind of shoved under the rug. It really has to do with capital efficiency of developing all the AI software that needs to be developed. Just taking traditional AI methods and trying to scale those, blitz scale in that direction, doesn't really work out very well, as we've seen. And so, the first and foremost goal for us is to kind of have a technology that's truly scalable toward, the really kind of extreme production requirements of a fully autonomous system. And so that's kind of step one for us, and something we made a lot of progress on via deep teaching. And the other component of our mission is to actually, really launch something before we get all the way to full autonomy. Right, full autonomy is a very difficult goal, and very capital intensive. But there's actually a real market out there today for L2 and L3 autonomous systems. These are cars that you'll be able to buy, in the coming years, or even now, that have some degree of autonomy. And actually, there's a huge benefit, from a convenience perspective, as well as the huge safety benefit of these partial autonomy systems. And so our go-to-market strategy is very, very much focused on that. And we see that as the ideal springboard for getting into the L4 market. Both because of the the revenue stream we can achieve today, as well as the kind of massive validation advantages we can get on these large-scale consumer fleets. And one other thing I'll mention is that it's not just about autonomous driving, right? There are many other markets that will benefit from the kind of software that's being developed for autonomous cars. There's drones, consumer robots, even retail automation. Essentially, anything that involves AI that interacts with the physical world will be a relevant market for us. And so, the way that we approach our customers, right, what we actually offer is a full suite of modular AI software, geared toward autonomous driving, right? So we actually have full stack capability from perception through control, but we modularize that for our customers. Very importantly, we are sensor and compute agnostic. What that means is that we still have to fine tune our system to a particular reference stack or a particular production stack, but we don't impose kind of hardware constraints. We don't come in with a black box solution, essentially. So this is very important, right, for being able to work with different vehicle types and fleet models. And lastly, we very much design our workflow around the software update paradigm, right? The notion that we'll be able to essentially not only put the software in multiple types of vehicles, you'll be able to update the software over time. So kind of significant, shadow mode fleet testing component, and the capital efficiency of deep teaching also plays a big role in our flexibility to be able to do that. So I'd like to spend some time just talking about like really what's at the heart of the differentiation here, and of deep teaching. And essentially what that is kind of exploiting the power of deep learning at scale, right, is a major component. And so neural networks can, we've seen some very impressive stuff with neural networks, right? And so they can definitely learn arbitrary concepts in very large data regimes. But typically you need quite a lot of data, even compared to a human, right? So you might need like 1,000 times more data than a human would need, and or more, and that data would have to be annotated for traditional methods to kick in. So what that means for computer vision, which is really at the heart of fully autonomous driving, at the very tail end, all of the corner cases are basically computer vision corner cases. You can't just solve them with LiDAR or radar. Computer vision is a very hard problem because human brain has evolved over quite a long period of time to be able to see, and even for the human brain, it takes like 2 years to learn how to see in the first 2 years of life. And so if you kind of do the math on that, in terms of how much data you're actually observing during that time, multiply that by 1,000 as a baseline, you might need even more than 1,000x more than a human for that task because of all the evolutionary pressure. But you might need trillions of images. And so, trillions of images is not something that, even if you have sort of the budget of, the biggest companies in the world, that doesn't imply that you can simply annotate trillions of images, right? And so really something has to happen with kind of state-of-the-art AI that would alleviate that. So just to give you an example, right? The cost of annotation for, let's say, 1 million images for semantic segmentation, which is kind of understanding every single pixel, right? These are images I've shown you in previous videos, and I'll show more. So costs about $4 million. Like that's like the cost on the market, right? It's assuming all the different efficiencies that have already been factored in by the companies that are offering these services. So it's quite a lot of money, right? But the cost of training on that data is only $50. So if you could somehow not have to pay this annotation cost, and you could only have to pay for the training, you'd have a massive advantage over your competitors, right? So it's several orders of magnitude in terms of capital efficiency. And so to illustrate kind of the advantages of deep teaching, here I'm showing you a video of this is just a random like dash cam video that we got from the internet. And here we're just showing the perception stack. This is not us driving, it's just somebody else driving, but you basically get, pixel perfect understanding of the world, right? And here we trained on something like 100 million images to be able to do this. So that's quite a lot of data, right? To annotate that data would be, yeah, I mean, it would cost like $500 million or something like that to annotate. So clearly that's not how we did this. And, we see actually better performance here than traditional methods can achieve for this task, even if you're talking about having the biggest budget in the world. So here's an example of some pretty, corner cases that we never anticipated, right? So this is like some weird ATVs in Los Angeles, or people doing crazy stuff, right, in strange poses, and the system works. And this is something that, again, we never anticipated this particular scenario, but if you train at scale, the system has been exposed to so many different things that it actually learns to generalize to even these strange situations, right? So you can imagine that that can be very beneficial for, essentially how to solve corner case. The typical workflow for autonomous driving is that you build a system, you take it out on the road, you drive it, you find corner cases, then you have to solve the corner cases, and then there's a lot of engineering churn that happens there. But if your system kind of out of the box already handles a lot of corner cases, your engineering time to get to production might actually be dramatically shortened, right? And so that's the reason really that we can build, pretty mature products in the space on a pretty small budget, really, is leveraging this kind of technology. And so, and this is not, I didn't just pick one video that worked well, right? There's, you can pick a random video and it's going to work about the same. So here we see a lot of different scenarios that are covered by our approach. And this can be used for for many applications, right? Not just again, not just kind of like basic 2D understanding of the world. You can also use it to actually infer the intent of the various agents on the road, like pedestrians, right? So in this case, you have pedestrians in those crowded urban scenes, and we're kind of tracking all these different key points. They're kind of meaningful key points in the human body, and we can use that to understand sort of how people actually interact with their surroundings, right? We can parse all the different object categories and really kind of like reverse engineer how humans behave in the world. And again, this is another problem that's very well suited for large scale training and deep teaching. And you can imagine this can have applications well beyond autonomous cars. We can also, by the way, it's not just about computer vision, right? There's other sensors that are also in the car. And I've shown previously the highway pilot system. They use the radar fusion system. Here we are fusing with a LiDAR point cloud. These are actually SLAM tracks from an Ouster LiDAR. And we are basically just doing a naive fusion of our kind of surround view vision system here with a LiDAR point cloud, and we're able to essentially create a high definition map purely algorithmically, which of course, as you might imagine, would have massive advantages in terms of the costs of maintaining these maps and updating them and etc. So, but this vision first approach is basically you kind of figure out how to quote unquote solve vision, right, and then use it to solve everything else. You can do essentially transfer learning to different sensor modalities and things like that. In fact, deep teaching can be applied directly as well to the other sensor modalities. So if we wanted to work with LiDAR data only, we can certainly do that using this approach. So we can also
just a quick time check, Vlad. We've got we're about 16 minutes at this point. So
yeah, I'm almost done.
Okay.
It's
all great stuff.
yeah, I'm almost done here. So yeah, I mean, actually that was it. So I just have a couple of corner case videos, so we can take questions, or we can go with everybody else. few questions after. So.
Okay, yeah. So we'll hold the questions to the end. I see that they're rolling in, which is great. Please continue to put your questions in the Q&A. And that's also why I'm kind of time checking folks, is to make sure we've got time to get to the questions. So let's roll to Herman, who will take us through CARLA, which is an open source simulation platform. And let's hear what we got going on there.
Awesome, thank you. Great talk, Vlad. Very nice to see what you guys are doing. Very interesting. So let me share my screen. Can you all see my screen?
Yep, we got it. You might want to go in presentation mode.
Perfect. Here we are.
Perfect.
So I'm Herman Ross, work at Intel Labs. I'm serving right now as a senior staff scientist and also as a program manager for simulation for autonomous driving. I'm going to talk a little bit about open source autonomous simulation using our platform, CARLA. In a nutshell, for all of you who have never heard of CARLA, you can see CARLA as an open and flexible API. So the idea is CARLA to have an SDK that can assist you in different tasks, from research to development and validation of autonomous vehicles. So our intention is to assist on all the tasks that are relevant in autonomous driving. So from deciding where to place sensors, to improve planning algorithms, forecasting algorithms, perception stack, etc., etc. And we try to offer a bunch of tools to help you with that, including the generation of content, different maps, ingestion of those contents, tools to automatically do validation of the final stack, etc. Here you can see, I hope the video runs smoothly through Zoom. So here you can see an example of what CARLA looks like today. This is one of the releases that we did last year. Ideally, you will find all the elements of the real world, vehicles, pedestrians, traffic signs, traffic lights, different type of roads, etc. So we're trying to model all level of complexity in CARLA and offer them throughout our API. Okay. Our mission is very simple. We really want to improve research, development, and validation of autonomous systems. We believe that tools such as CARLA are a requirement in order to make decent progress in autonomous driving. We believe that autonomous driving nowadays, the way it's executed, is too complex, too expensive, that we need to keep improving simulators. We need to keep improving the use of synthetic data in order to enable faster turnaround in autonomous driving development. Also, we see CARLA as a tool to democratize access to autonomous driving development. So we believe that the problem is so impactful for our society that we need to hear from pretty much everybody. So not just from top companies, but also from small labs that could provide interesting perspective and ideas. And for that, definitely not everyone has the resources to create a fleet of vehicles and to do this kind of testing. So we believe an open source simulator helps a lot to participate in this game. Going through some basic features, so a sort of introduction to CARLA. So it's a modular, CARLA has a modular design. So it's a server client architecture that can be scaled up using multiple nodes. So you can divide the processing of the simulator into different modules that can run independently. You can have one module controlling traffic simulation, another module controlling weather patterns, different modules controlling how pedestrians are going to be moving around the vehicle, etc. For that, we provide two APIs, one in C++ and one in Python. And as you can see on the right side, we are making an important attempt to have these APIs to be as simple as possible. We invest a large effort in providing realistic sensor simulation, not just from a camera perspective, but also other modalities like LiDAR, radar, GNSS, IMU, and all the typical sensors that you find nowadays in an autonomous car. We attempt to provide an extensive library of assets that we put available for everyone for free for both non-commercial and commercial purposes. So we have hundreds of vehicles, pedestrians, traffic signs, maps. We also release our maps. I think the most important part is probably our flexible query engine. So in CARLA, everything that you see can be controlled and can be queried. So you can query speed for everything. You can query the position of every single object on the scene. You can get their position, location, their extent. You can make them disappear. You can switch off and on any independent objects. You can change weather configuration, weather patterns, rain, sun visibility, you name it. Everything is controllable in CARLA. We have an important role to play in how traffic simulation is done. So we offer very different solutions on traffic simulations, starting from modules where you can parameterize how different vehicles are going to behave, if they're going to skip some traffic rules, with which probability, etc. We try to provide realistic physics through integration with third-party tools like CarSim and others. We also praise ourselves in the generation of interesting tools to procedure generate maps from external sources like OpenStreetMap and OpenDrive. So if you don't want to design your own map, you can leverage our tools to select a region of the world, and we will produce a simple map for you that you can use for your experiments. We put a lot of effort as well in integration with external tools. So CARLA is a white box that can be integrated with pretty much everything. That includes existing open source AV stacks like Autoware that we'll hear about, and many others. So CARLA definitely provides integration with all these solutions. One of the critical aspects of CARLA is its community. So we have been growing a strong community around the CARLA ecosystem since 2017, 2018. We can see the progress of the community through the number of people who like the project in GitHub, through the number of downloads that recently reached 2.5 million last year, through the number of scientists who cite the paper, the number of companies that decide to embrace CARLA for both research and product generation, and also through the number of people that come to our communication platforms like Discord, the CARLA forum, etc., which keeps growing every day. So we're pretty happy about how the community has been engaging in the use of CARLA. Here's a few examples of how CARLA is used for research purposes, for proposing new ideas, running new experiments, both by non-commercial like academic entities and commercial entities. We are very happy to see all the progress that the people are making using CARLA. One of the most interesting activities that we put together last year was the CARLA Autonomous Driving Leaderboard. Something that we noticed very early in the game was that it was very hard to compare autonomous driving stacks. We have seen in different places, like in California, we have the DMV reports that different companies do optionally, so they can release their metrics to DMV. But all of them are hard to put in context because different companies are testing in different places. They have different policies on how to declare disengagement and so on. And we decided that we needed to provide a common test bed that could be used to better understand which modules, which algorithms are bringing real progress to the autonomous driving problem. And we created the leaderboard, which is basically an online platform that participants can apply to. This is free to use. Basically, it consists of driving a set of predefined routes that are not known in advance. You just have to drive a couple hundred kilometers from point A to point B. We're going to be presenting you with a set of traffic situations like the ones you can see in this video. And your vehicle needs to be able to react to them. We are using a set of metrics to evaluate your performance, including, well, how close you got to the target destination, and also we're going to be discounting points according to the number of infractions that you commit. So if you hit something or you get out of the way, etc., you're going to be discounted. We're running this activity all year round, 24/7. So teams around the world can just apply, and we will evaluate their AV stacks automatically. From time to time, we're putting together this event that we call the CARLA Challenge, which basically is just a snapshot in time, typically associated with a conference, just to try to take the latest picture of the state of the art and trying to find out what are the newest techniques this season that could be used to make progress. So we're very happy with all the progress that the leaderboard is bringing. We have seen constant improvement every year. So scores are going up quickly. I think this is really bringing a lot of progress to the community. So just as a summary here, the leaderboard itself as a competition requires you to drive around 173 kilometers, okay, in order to get the full evaluation. And this happens across different weather patterns, and you're going to be finding multiple traffic situations that have been borrowed from the NHTSA crash analysis. This year, in the latest challenge that we organized, last year in 2020, we have around 45 teams, which in total spawned around 6,000 hours of simulation, drove almost 7,000 kilometers. If you are interested in all this stuff, I would recommend you to visit leaderboard.carla.org, where you can find all the details and the setup on how to participate. This is from my side. So if you have any questions, feel free to ask. Well, you are also invited to join us through our community in Discord, GitHub, or our website. Thank you.
Awesome. Thank you, Herman. Great presentation. All right, so we'll turn it over to Christian John, or CJ, as we know him, to give us an overview of the Autoware Foundation solution.
Great. Thank you, Brent. Just pull up my presentation here. Okay.
I think we're looking at the presenter's view rather than the
okay.
The other side.
Sorry, how do I?
Oh,
give me a second. Sorry about that. Is that better?
Yeah, try clicking on that. There you go. You're good.
Okay. So I'm going to give you guys an overview of Autoware, both the Autoware Foundation and some insight into the Autoware project developing a autonomous driving software stack. Autoware was originally created by Shinpei Kato at Nagoya University with his students, and decided to open source the software in 2015. It's based on ROS, so it leverages a lot of the robot operating system capabilities around functionality like the drivers to various sensors, and now in kind of ROS2, DDS, middleware solutions. It's a complete autonomous driving stack. I'll go into some details on what the stack looks like and the functionality that we've supported. Independent of vehicle type or electronics. So it's been basically now ported to many different types of compute platforms, integrated into numerous vehicle types. We think the number of projects using Autoware is in the hundreds now. And the Autoware Foundation was set up as an independent foundation to help govern the advancement of Autoware technology and basically to grow the ecosystem around the open source software. And I'll give you some insight into what the foundation structure and the membership looks like. Lastly, Autoware is completely open source, licensed under the Apache 2.0 licensing framework. And what we're trying to do with Autoware, it's a lot more than just the AD software stack that's running on the vehicle. In order to implement a autonomous driving system, there's many components that have to be brought together from an end-to-end perspective. So we, in the Autoware Foundation, look at, in addition to the AD technology itself, all of those components around the autonomous vehicle that need to be integrated for a system to be considered safe, secure, reliable, addressing all of these types of topics. So from the infrastructure side, some of the key things that we look at, how to integrate with communications infrastructure, V2X technology, for example, vehicle to infrastructure such as signal lights and so forth is becoming an important part of smart city, advanced road networks, and how that ties into autonomous driving technology will be an important part of what we look at. Of course, map solutions have to be integrated with the AD technology, and looking at how to do that in such a way that we can scale this solution globally across many different markets and many different applications. We work closely with governments to influence how planning is done for future AD enabled services and applications in cities, and how to regulate and to inspect AD technology. That's something that's going to be very important as autonomous driving scales up. And then the other aspect is service providers. As you start to look at how do you operate a AD system, there's many cloud-based services and applications that come into play, and that again needs to be integrated with the AD stack. And that's something that we'll look at as part of the work that the foundation does. And then clearly the technology itself, running an AD stack, really to scale that up in the future, there's a number of topics that have to be addressed around the cost of the implementations, the power consumption. We are at just the inflection point of this technology taking off, and there's still quite a bit of work that has to be done in really optimizing the solutions to address these topics around cost and power consumption to really help drive the volume of AD technology. And if you take a look at the membership base of the Autoware Foundation, you'll find that the companies that are involved are really touching across all those aspects of the ecosystem. Whether it's the development of the software technology, the OS, the middleware, companies involved in deploying or defining how AD technology is going to be used in the next generation of smart cities and smart roadways, such as the US Department of Transportation is very much involved in using Autoware for a lot of the work that they're doing around the CARLA project. And we're starting to see more and more companies that are using Autoware in their commercial implementations for end applications also become more active as far as helping to define the future of the technology. Zing Robotics is a good example of one of those that is now working very closely with the Autoware Foundation. I'll touch a little bit more on that later and how we're working with these companies. The organization is consisting of a number of steering committees which are deriving the work that is done in kind of the open ecosystem. So within the foundation, we have a board of directors, of course, a strategic planning committee, which helps to define the direction for the foundation. There's a technical steering committee that really is responsible for driving and maintaining the different work group efforts from the standpoint of aligning those with what really needs to be accomplished in the open source projects that the foundation is cultivating. And then an operations committee that helps tie together all the aspects of what the foundation is doing. The technical steering committee has basically spun off a number of work groups now that are tackling different aspects of the open source AD technology development. We have an ODD working group, or operational design domain group. Of course, the software working group driving the open source software development, and then a hardware group that is looking at reference implementations of compute ECU units that are integrated with sensors to implement Autoware in various ODDs. And I'll touch a little bit more in detail what that means in some later slides. And then the key projects that the foundation are driving are really around the Autoware software stack development, and then everything that goes around that. So the original project, Autoware.ai, was implemented on ROS1 and really launched as kind of an R&D platform for AD technology. Autoware.auto is the project we're really focused on now. This is now being implemented on ROS2, and this is where you have things like DDS, or data distribution service, integrating the architecture to optimize data flow, and the architecture of the software is really structured from the standpoint of looking at scaling into commercial implementations where safety certification and these types of things will have to be addressed by the software. And then the Autoware.io projects are really around interfacing to the Autoware software stack. So think of this as anything that is sort of kind of a third-party solution, whether that's simulators, that's map databases, hardware, sensors. All of these types of things need to interface with the software stack. So we're looking to define the ways that all of these different solutions in an open source type environment can work with the Autoware stack. So looking at using open source simulators, as which was talked about before with the CARLA simulator, as well as others from LG and Tier 4 as a simulator provider. And then all of the other components that are required to build a system, validate it, and basically deploy it commercially. Okay, the Autoware software stack, as I mentioned, is a complete AD solution, AD software stack solution. It has all of the elements for the sensing, perception, planning, control functionality, and localization functionality as well. So what we do here is we are architecting these modules in a way that they can be used as is from Autoware. We also have defined the APIs between these different modules. So some companies can come in if they're specializing in something like planning, control type functionality. They can do drop-in implementations of their proprietary software. But the fundamental idea is that Autoware.auto provides you everything you need to go and start using AD in a particular application. And the approach that we're taking to develop this technology is that as this is an open source project, we're getting contributions to the Autoware.auto project from players, individuals all over the world. So what we have set up in the foundation is a project structure where we're developing and advancing the technology based on a set of well-defined problems, where the individuals participating in the development have a good understanding of the algorithms, the functionality that have to be implemented in order to address the requirements for that application, and then verify it in that particular operational scenario. And the way we do that is we talk about operational design domain-based development in the foundation. The idea is being, if you look at the different types of scenarios that you can deploy AD technology in, there's a wide range of environments that you'll operate in, ranging from restricted environments, which are fairly constrained, well-defined, limited number of actors within the environments, as far as pedestrians and other vehicles to worry about, ranging all the way to the city center type deployment. So this is the L4 robo-taxi and dense urban type environments where you really have to deal with very complex operating conditions. And the technical requirements as far as what the AD stack has to support as you go from one extreme to the other is quite dramatic, as far as the number of sensors required to adequately understand what's going on in the environment, which then drives a lot of the complexity in the types of algorithms in the localization, perception, planning and control, and so forth. And in order to make this a more manageable problem for the open source ecosystem to develop, the approach that we're taking is starting more from the constrained, dedicated, geofence type ODDs, incrementally building up the functionality of that software stack to address those operating conditions, and then over time advancing to tackle more complex ODDs, with the ultimate goal that Autoware will be able to support all of the features and functionality required to do L4, L5 type implementations in those city center complex environments. So the roadmap that we've defined so far for Autoware in that sort of trajectory of getting towards the L4, L5 in the urban environments is, we started originally with autonomous valet parking. And the reason we did that is this is typically a well-constrained environment. It's low speeds, and there's a very limited number of actors that you'll run into in this particular environment, as far as pedestrians and other vehicles. And again, operating at very low speeds. So this was the basis of what we implemented in Autoware.auto in what is now released under the version 1.0 release, and becomes the basis now of everything that we're going to do going forward. The foundation has selected 2 additional ODDs that we're focused on right now: cargo delivery, so logistics, material handling, the environments here are starting to get more complex, and one of the particular cases that we're working on very closely with Zing, as I mentioned, is using Autoware.auto for demonstration of autonomous baggage handling. So this would be operating in airport environments, near aircraft, baggage rooms, and so forth. But there are many other applications of cargo delivery that are currently being worked on around factory material handling, logistics, and so forth, as well as even some sort of last mile delivery solutions that could operate on public roads as well. The other key ODD that we're focused on right now is racing. And the reason we decided to do this is twofold. There's really a lot of advanced algorithms that you need to develop to basically operate at high speeds. So really pushing the performance of the perception, localization, and control functionality in the stack. But then also from the standpoint of engaging a broader ecosystem of developers. There's a lot of interest in racing in the university community, and that's where we're trying to get more engaged with research and development and the work that's being done in universities, and bring those developers into the Autoware ecosystem, and then participate in these types of racing activities such as F110 and the Indy Autonomous Challenge is one that we're closely engaged with Autoware right now as well.
Just a time check, CJ, just to make sure we're going to have time to cover Q&A. So
okay, I'm pretty much done. So I just wanted to wrap up with that last point of, we're working with the F110. We're bringing together the university ecosystem to basically bring Autoware onto the 1/10 platforms, but then also working with some of those same university teams that are involved in things like Indy Autonomous Racing to bring Autoware into full-scale racing. And the idea here is that there's a number of future racing events that will be based on Autoware that the teams can start to participate in. And we'll use this as the basis for continued advancement and development of Autoware functionality. All right. Thanks.
all right, thank you. And I have to thank Herman and Vlad. They've been doing a fantastic job of answering questions as they come in. so we've got a lot of them covered. There is a question outstanding here. I think it's for Vlad, for Helm, or maybe actually this is for CARLA. It's about simulating Class 8 tractors and trucks.
Yeah, it's indeed tricky because typically those come with a lot of access, right? Making the vehicle dynamics a bit more complicated. We depend on external modules to do co-simulation for those. So it's something that some folks have been doing in CARLA for their own benefit. We don't have yet like our own open source solution for that. But it's basically because of the vehicle dynamics of those kind of vehicles that are a bit more complicated.
Okay, makes sense. So okay, CJ, it looks like you're answering this, but maybe you can just go public with it. How can municipalities contribute?
Yeah, so either through joining the Autoware Foundation, and as we showed, there's multiple levels of participation in the foundation, but the work groups are actually open to anyone to participate. And what you will find, we're now working on a update to the Autoware Foundation website where it's going to be easier to see what opportunities there are around the work groups to participate in things like the ODD definition. I think that's an important one where municipalities would be interested in participating in the definition of the scenarios and the requirements which are going to drive the AD technology development. There'll be work that can be done in the we haven't launched it yet, but we're about to launch a simulation work group, which is really looking at that end-to-end simulation pipeline of once you've defined the scenarios, you need to be able to simulate them and to assess the behavior and safety of the AD in those scenarios. And that's, again, another one where I think municipalities will be very interested in understanding the not only how the AD is performing, but contributing into the definition of what is considered safe behavior in different scenarios. And then, like I said, joining the foundation, participating in driving the direction of the technology going forward, that would require a premium membership level in the Autoware Foundation to participate in the work groups. And there's information on the website how to join at those different levels.
Cool. All right, so we're about out of time, and I think most of the, if not all of the questions have been answered. I noticed that Brad posted both in the Q&A and in the chat, and Herman answered Brad's question there. So if you're looking for it, that's where it is. So we will go ahead and wrap up for today. I want to thank everyone for attending, and I really want to thank our presenters. Gentlemen, that was very, very valuable information. This has been recorded and it will be made available to the community. And if there are questions that have not been answered, please feel free to share those on the meetup page and I will forward them to the appropriate speakers, or you can reach out to them directly. It looks like we have one more here. ASAMnet is working on OpenSIM and Open Label standards in addition to OpenDrive. Would be great if CARLA and Autoware supports this also. Are you guys familiar with ASAM.net?
We're definitely familiar with ASAM. We work closely with them. Definitely once the open label concept is solidified, we will adopt it. We're definitely looking into OpenSIM and other simulation standards.
Perfect. All right. All right. Well, gentlemen, I will let you go. Thank you so much for your participation, and thank you to our attendees for participating. We will advertise the next Self-Driving Cars 101 event for May here shortly, and I want to thank everyone for participating today. Enjoy your week. Thank you.
Thank you.
Bye-bye.
Bye.
Bye.